The James Webb Space Telescope has captured something truly astonishing: lights that appeared to shine like those from a distant city, located 4 light-years away. This discovery has reignited global interest in the possibility of extraterrestrial life. The telescope focused its gaze on Proxima Centauri b, the closest known exoplanet to our solar system, and detected strange, bright flashes. Could these lights be signs of an alien civilization? The question has sparked both wonder and serious scientific investigation. For decades, both scientists and the general public have dreamed of discovering life beyond Earth. Any credible sign pointing toward that possibility is met with excitement and curiosity. The James Webb Space Telescope, with its advanced capabilities, may have brought us closer to that dream. While scanning deep space, the telescope detected unusual light emissions on Proxima Centauri b, lights that resemble those of a technologically advanced city. The implications of this are enormous, suggesting that intelligent life could exist and organize itself in ways we are only beginning to imagine. These mysterious lights, observed from a planet 4 light-years away, have left NASA engineers in awe. They wonder how long the lights might have been present, silently glowing in the cosmic dark, waiting for our instruments to evolve enough to see them. David Kipping, an astronomer from Columbia University, emphasized the complexity of the planet where these lights were detected. Unlike most rocky planets that absorb sunlight and re-emit energy as infrared radiation, Proxima Centauri b behaves differently due to its unique relationship with its host star, Proxima Centauri. The discovery highlights the importance of the James Webb Space Telescope. Its ability to detect infrared wavelengths played a vital role in capturing this unusual behavior. This kind of detection is key to understanding Proxima b's atmosphere and evaluating its potential habitability. Researchers plan to continue observing the planet using the telescope, diving deeper into its atmospheric characteristics and investigating whether it could support life. One of the James Webb Telescope's greatest strengths is its sensitivity to infrared light. This allows it to observe what happens on Proxima Centauri b even on its night side, where traditional telescopes would struggle to detect faint signals. The James Webb can pick up even the most subtle glimmers of artificial light, especially if that light falls within a narrow frequency band, unlike the broader emission of natural starlight. This makes it ideal for confirming whether the suspected lights are, in fact, artificial in origin. Proxima Centauri b shares a dynamic relationship with its parent star. Like Earth, it experiences day and night cycles as it orbits its sun. But due to its potentially thin or non-existent atmosphere, the differences in temperature between its day and night sides could be extreme. If Proxima b lacks an atmosphere, its day side might become extremely hot while its night side freezes, creating stark thermal contrasts. These variations provide crucial insight into the planet's composition and atmospheric makeup. Thanks to its infrared imaging capabilities, the James Webb Space Telescope can analyze Proxima b's thermal emissions, helping scientists understand how heat is distributed across its surface. Interestingly, the telescope's Earth-based orbit lines up closely with Proxima b's orbital period, allowing researchers to monitor its day-night cycle every 11.2 Earth days. If an atmosphere is present, the next step would be to analyze its chemical composition to assess whether it can support life. Gases such as oxygen, water vapor, and methane could suggest a habitable environment. Detecting these elements involves studying how light passes through the planet's atmosphere, an incredibly complex process. Although the James Webb Telescope isn't specifically optimized for oxygen detection, it can identify other important components like ozone, water vapor, and carbon dioxide, which together can point toward life-friendly conditions. Ozone, for instance, is a strong indicator of a stable, oxygen-rich atmosphere. As scientists continue to process the telescope's findings, the search for distant worlds that may harbor life becomes increasingly promising. Still, it's important to recognize that the James Webb Telescope has limitations. It can only study a select number of exoplanets near Earth in detail. For more advanced atmospheric exploration, astronomers will rely on upcoming ground-based observatories, such as the Extremely Large Telescope, ELT, which is expected to begin operations in 2028. The ELT will offer a much closer look at exoplanetary atmospheres, providing even greater detail and accuracy in determining whether other planets could sustain life. Until then, the James Webb Space Telescope remains one of humanity's most powerful tools in the quest to understand our place in the universe. Its discoveries continue to bring us closer to answering one of the most profound questions we've ever asked: Are we alone? Despite its current limitations, the Webb telescope continues to deliver valuable insights that are gradually transforming our understanding of the universe beyond our solar system. Its contributions are not only shaping our knowledge today but are also laying the groundwork for future discoveries. Looking ahead, researchers are developing next-generation space telescopes equipped with advanced technologies specifically designed to overcome the challenges of observing distant exoplanets. One of the biggest obstacles in exoplanet detection is the overwhelming brightness of their host stars, which often outshine the planets by many orders of magnitude. This makes it incredibly difficult to capture the faint, reflected light that is essential for analyzing planetary atmospheres and detecting signs of life. To tackle this problem, scientists are working on innovative methods to reduce starlight, thereby improving our ability to observe the planets orbiting those stars. It's much like raising your hand to block out the sun to see something more clearly. By diminishing the star's light, we can enhance the visibility of objects around it. One technique that shows promise is the use of coronagraphs. These are instruments placed inside a telescope that block out the star's light while allowing the light from nearby exoplanets to pass through. By manipulating the shape and direction of light waves, coronagraphs significantly reduce glare and make the dim planetary light detectable. Another groundbreaking idea in development is the starshade, a spacecraft shaped like a giant flower that operates in tandem with a space telescope. It is positioned tens of thousands of kilometers away from the telescope and is designed to block out the starlight before it even reaches the telescope's optics. This method could be particularly effective in observing planets located within the habitable zones of their stars, regions where liquid water might exist and where life could potentially thrive. However, the use of a starshade requires remarkable accuracy. The alignment must be precise down to fractions of a millimeter over vast distances, making it one of the most challenging space maneuvers ever attempted. In addition to perfect alignment, engineers must also overcome other space-specific challenges, such as the miniaturization of components, maintaining energy efficiency, and ensuring the equipment can survive extreme conditions in space. Yet, the potential payoff is enormous. By successfully capturing and analyzing the light from these far-off worlds, scientists could detect biosignatures, specific combinations of molecules like oxygen, methane, and water vapor that may indicate the presence of life. These discoveries would not only provide evidence of life beyond Earth but would also offer clues about the conditions and processes that make such life possible. Beyond simply detecting these planets, future space telescopes could also be equipped with advanced adaptive optics that compensate for the distortions caused by Earth's atmosphere or movements of the telescope itself. These adaptive systems would allow for sharper, more detailed images. When combined with light-blocking technologies like coronagraphs and starshades, these upgrades could enable us to map the surfaces of exoplanets and study their climates in detail. The ability to create such detailed observations represents a major leap in our search for life in the universe. The future of space observation holds incredible promise. With each technological advancement, we move closer to answering one of humanity's oldest and most profound questions. Are we alone in the universe? As our instruments become more sophisticated, our capacity to explore and understand distant worlds increases, potentially leading to discoveries that could redefine our place in the cosmos.